Hello? Hey, everyone. I was really hoping we were going to run into Justin Bieber's soundtrack. They had some great music playing. I was hoping we were going to break through a wall or something. But,
keep the music playing. I was enjoying that.
Welcome, everyone. We have the dubious 1 p.m. after lunch hour session. We hope that you're going to be as excited for this presentation as we are. The title of this is Making Your Cloud Service Google Fast. Some quick intros. My name is Weston Hutchins. I am a product manager on the Google Cloud Platform team.
My name is Mandy Waite. I'm a developer advocate for the Google Cloud Platform.
She's my dev rock star for today. And today's talk, it's really hard to talk about a topic as deep as performance in 30 minutes. So Mandy and I have cherry-picked a few tips and tricks. We're going to show you guys some demos on top of Google Cloud Platform and how we can make your app as fast as possible, leveraging the infrastructure we use at Google. So we've broken down this into 4 topics. The first is I'm going to tell you a little bit about why fast matters. Then Mandy's going to take over and tell you how we think about fast inside Google, how we leverage the infrastructure to build our world-class apps today. Then the meat of the discussion is going to be around two topics. One of them is measuring fast and how you should think about correctly measuring the performance of your application. And then Mandy's going to take over and tell you guys how to scale out and scale fast so you guys can be the next secret app that has 1,000x growth in your first month of use once you reach the front page of Hacker News. So why fast matters? You might be thinking, duh, of course it matters. But I always like to throw out some fun facts just to talk a little bit about what the impact of performance can have on your users. There was a study done a little while ago that Google actually went out and intentionally induced a server-side lag delay for every result that was coming into the Google search page. And they wanted to measure the behavior over a period of 3 weeks of how often users were searching with various amounts of lag built in. And what they found was pretty interesting. If you just increase the amount of lag by 400 milliseconds, it would reduce the amount of searches by 0.6%. And when you're talking at Google scale, that's actually a huge number. It ended up being about 8 billion searches a day at the time this study was run. Even more so, this study also figured out that users are impatient. And you guys probably don't need me to remind you about that. But they found that 1 in every 4 users will abandon a web page if it takes more than 4 seconds to load. And given the competitive nature of performance nowadays, I can only imagine that this number is likely to decrease over time. Mobile apps are also important as well. It's not just websites that we have to start thinking about. There was a study that was released just this last week by App Dynamics, which is a leading performance monitoring solution out there. What they found when they surveyed a bunch of users was that performance was the #1 top frustration when using mobile apps and websites. 86% of users deleted or uninstalled at least one mobile app because of problems with application performance. Now, there is a silver lining there. They also found out that when users are happy with your performance, they're going to spend more money. 30% of users said they would spend more money with an application that had greater performance over its competitors. So there is real incentive here for you guys to spend the money, spend the time, speeding up your application, and making it fast for your end users. And with that, I'm going to hand it over to Mandy, who's going to talk about building a culture of fast at Google.
Thank you, Wes. So fast is at the core of pretty much everything that we do at Google. Well, nearly everything. And users of our products and services are used to experiencing a consistently fast performance from all of our products and services. You can offer that same experience to your users by using Google Cloud Platform, because Google Cloud Platform runs on the very same infrastructure as services such as Gmail, Google Search, YouTube, and all of our other products and services. So let's talk about some of the philosophies behind fast at Google. In order to meet the demand of modern-day applications, the traffic demand of modern-day applications, you need the ability to scale fast. And scale fast is something we're going to talk about in the last section, as Wes has already mentioned. And App Engine, our platform as a service offering, which we'll also talk about shortly, that kind of epitomizes the notion and the principle of scale fast. So we have an example of that coming up soon. The ability to measure fast allows you to gain insight and understanding of the very complex nature of modern-day applications running in the cloud. And Wes is going to talk to you very shortly about some specific examples around latency and also introduce you to some tools that we're going to be making available to users of the Google Cloud Platform. And then there's the ability to innovate fast. Now, this has really been core to our ability to actually keep ahead of the game when it comes to handling the, as you can pretty much imagine, handle the massive amount of traffic demand that we have on all of our products and services. And not just on the products and services themselves, but also on the infrastructure that runs them. So we've innovated rapidly over the last 15 years. And this is a timeline of some of the things that we've introduced, white papers and such like. Bigtable is our massively scalable NoSQL data store. And many of our services use Bigtable directly. And in fact, App Engine itself was built around Bigtable. It was actually built around Bigtable to use it specifically. So users of App Engine had direct access to Bigtable as the App Engine data store. That data store has now been made available to users of the cloud platform directly from anywhere, any user from anywhere, from any application, as the Google Cloud Datastore. Then there's Dremel. Dremel is an analysis tool that allows you to run interactive queries across massive data sets. And we're talking about terabytes here, billions and billions of rows of data, and to get results back in seconds, not minutes or hours, as you would do with a MapReduce. Dremel is available externally via the Google Cloud Platform as the BigQuery service. Then there's Colossus. Colossus is our second-generation file system, and many of our data services are built on top of Colossus. Colossus has been made available to cloud platform users for many years now as Google Cloud Storage. Then there's innovations at the infrastructure layer, and we're going to talk about Andromeda shortly. So we have scale fast, we have measure fast, and we have the key of innovate fast. All of these things make to a wonderful Google Cloud Platform experience when you use it. Not only do you get all of these when you use Google Cloud Platform, but you also get fast connectivity to the rest of Google at no extra cost. So if you want to consume Google search results, YouTube videos, maps data, finance data, you can do so at no additional cost. If you were using another cloud provider, you would probably have to pay some additional charges in order to get that data into the cloud. So I want to talk about how some of the changes that we've made to our infrastructure will benefit cloud platform users. And I'm going to do this in the context of a product, not a product, a feature of our network infrastructure, our network virtualization layer called Andromeda. And Andromeda provides all of our virtualization needs. So Andromeda is our network-based, SDN-based, software-defined networking-based network backbone infrastructure. It provides many benefits to us in terms of quality of service, fault tolerance, and lower latency. But it also provides all of our virtualization services, and that shows up in the form of virtual networks for Google Cloud Platform users. Now, Andromeda was not built as a Google Cloud Platform product. It was built specifically to address the needs of our own internal infrastructure. But because Google Cloud Platform runs on that same infrastructure, it gets the same benefits when it comes to high performance, security, isolation, and availability. So we built Andromeda really to address the ever-increasing demands of moving traffic between storage and compute, something that traditional networking infrastructure really wasn't able to keep up with. So as you can imagine, Andromeda is also going to give us better throughput. So we have this graph here, probably a bit of an eye chart for some of you guys. On the y-axis, we have relative performance, where higher is better. And at the bottom, we have compute engine instance types, compute engine virtual machine instance types. Standard is the standard memory configuration. And then we have 1, 2, 4, and 8 cores. So these are bigger machines as we go along to the right of the x-axis. The blue bars represent the average performance, the average throughput for what we had before Andromeda, the non-Andromeda average. As you can see, this is fairly static across all 4 of those machines. The red bar represents Andromeda average, the average we see with Andromeda. As you can see with the smaller instance, the 1-core instance, we get almost double, 2x throughput performance on that particular type. When it comes to the 8-core instance, we get roughly 4x performance, 4x improvement in throughput on single-stream TCP connections. So this makes these larger instances perfectly suited for network I/O-intensive workloads, such as maybe Hadoop, HPL, any kind of application that is extremely sensitive to latency. And just to mention as well, Andromeda is our network infrastructure. It's available in all of our zones on Compute Engine, in all of our regions. And on the subject of latency, was going to be the subject of latency, I'm going to hand you over to Wes, who's going to talk to you about measuring fast.
Thanks, Mandy. So I wanted to spend a little bit of time talking around what it means to measure an application, because you guys can make all the performance improvements in the world, but if you don't know how they're impacting your application, you may be doing something bad under the covers that you need to know about. So normally when I ask a web developer, I say, hey, John, can you go tell me the performance of this particular web page or application page, homepage loading screen that's coming up? And the first number they almost always come back with, which is the easiest thing to report, is average response time. A lot of monitoring solutions report this to you. But the thing I want to point out is that this may look good. 200 milliseconds may not seem that bad. But that's only average. How do I know if 10, 20% of my customers are seeing loading times of greater than 4 seconds, and then there's a lot of people seeing really fast requests? And average response time is misleading. And that's the real point I wanted to try to make here, is that anytime you report on average, it works well when you have a model that follows a normal distribution curve. When you see things where it's like a few requests that are very fast, most of them in the middle, and then a few tailing off at the end. But the problem is that most applications don't behave like this. In fact, this is actually a more typical latency analysis curve that you would see as part of your web app or mobile application. And the reason is this behaves a little bit more like a step function, and it actually makes a lot more sense when you think about how an app is architected and built. At the very beginning of the curve, you see most of the requests. This is a good thing, and this is because most modern web applications and apps have some form of caching. So users go and hit your web server, the cache serves the request, gets the data locally, and is able to send it back to the customer really quickly. But then what happens when you have a cache miss? Well, that's when things take a little bit longer. And so if most of the users are hitting the cache, only a few of them are missing it, and this is where you start to see the decrease in the number of people that are experiencing longer latency. So as I said, it behaves a little bit more like a step function. Finally, at the end, you start seeing things that we call the long tail. This is where you need to start really paying attention to some of the stuff that's going on. This is the problematic areas that you may see, specifically this guy. If this bump right here starts to spike, it's usually indicative of a problem. It could be, your servers are overloaded with traffic and they're starting to fail. It could be a third-party API that's timing out. It really could just be a programming bug. We see a lot of examples where some user comments end up scaling out and causing really slow response times for a number of users. So oftentimes it could be a variety of these things, but you really want to start paying attention to the tail. Googler Jeff Dean sort of says this best. He goes, even if your application appears to be performing fast, always be aware of the end-to-end spectrum. Don't just look at average. Don't even look at 50th percentile. Make sure that your long latency tails are performing well. So if averages aren't the answer, what is the answer? Typically when we talk about performance, I love it when people tell me percentiles rather than averages. And to give a really quick, simple example, imagine my application got 10 requests that were served. Notice that the average of this is 102 milliseconds, but it actually doesn't say anything about how many users are seeing average response times of 102 milliseconds. And if I go and take the 50th percentile of this, I can then say, oh, well, half of my customers are experiencing latency 50 milliseconds or greater. And this gives me much more confidence in the range of users that are seeing good and bad performance on my application. So quiz time. If I was to show you guys a quick little graph of two applications that have a latency curve that looks like this, which do you think is better? I hear two, I hear one, I hear a little bit of both. You're probably sitting there saying, you just told us that averages aren't the right thing. So, of course, the answer is, it depends. And that's true. In this particular example, this is actually real-world data that we took from two apps that we were running internally at Google. And we found that even though the average of app 2 was a little slower, the 95th percentile was further in. So we got really reliable, predictable, consistent performance, and it was under that 4-second magic time. App 1 had some attrition rate from people that didn't want to wait for these long requests. So really, the whole point of this slide is to start thinking about the range of performance across your application, and also realize that good performance engineers try to bring forward the bars. They try to move these bars a little bit left in terms of the percentile graphs. But any change that you make can have an adverse effect on the other percentiles. So always keep that in mind. You might make something better for the 50th percentile, which will impact the 95th percentile. And those are just performance trade-offs that you're going to have to figure out what the right solution is for your application. So I'm going to come over here and give you guys a quick little demo. You saw some of this in the keynote today, and I just wanted to show you in a little bit more depth what was going on. We recently announced a product called Cloud Trace, and I want to show you how that works. This is a tool designed to help you debug long latency tail apps. So I've loaded up the Walk Share app, and let me exit out of the comments here. It's a beautiful app that says, "This is where I walk." Look how peaceful that looks. Yeah, sorry. Thank you, Mandy. And it allows you to go and comment and figure out, OK, well, this is a nice walk, or it's not a nice walk, or I've done better than that. So I'm just going to go ahead and add a test comment in here. And when I hit post, this is exhibiting some pretty long characteristics. There was a delay there. It wasn't immediate. And I noticed when I was using this that the more times I had comments on the page, the more it was lagging. And so Cloud Trace is a tool designed to help you figure out what's going on there. From under the monitoring tab, you can go into the developers console and click on traces. And this is a tool that allows you to see the requests that are coming into your application in real time. So if I was to go and filter to say, let's take a look at things in the last hour, and I can even do some searches. And then I'll sort by latency to see the slowest latency request. This was actually the recent request that I made in an earlier session. I'll go ahead and pull it up because the graph should look similar. But for every single one of these comments, the Cloud Trace tool tells me how long this particular request took, and then gives me a list of the RPCs, or remote procedure calls, that were made during this request. So it's really easy for me to pull out and say, all right, well, I can obviously see the problem. I'm doing a bunch of synchronous data store calls in a loop, which is causing it to basically block on the number of comments that I have. In fact, if I even go and click on some of these other tabs, I can see that the majority of my calls are all in this datastore.get method. And the fix for this is pretty simple. I ended up pulling up some code here. I'm not going to make the fix, but what I wanted to call out was I noticed that everything that I was doing here in Datastore was via synchronous method. We actually offer async counterparts to most of these. So I fixed the version of the app. I ended up pushing that out to production using the async APIs. And what I got was a very different picture. You can notice that most of my Datastore calls are now parallelized. I'm doing some puts in addition to some gets here. This greatly sped up the overall end-to-end performance of my application. And a few more notes on Cloud Trace. Right now, this is a product that's in limited preview. We're going to support it for App Engine right out of the box. 0 configuration. You turn this on. You get these traces for you automatically. And as we start to roll out the lifecycle of this, we really want to extend this across not just App Engine, but Compute Engine as well, and give you guys detailed analysis on what these RPC calls are doing, what code line was calling them, and really take a deep look into what your service is doing for every single request that's coming in. Now, before I hand it back to Mandy, I wanted to impart with you guys a few little tips and tricks for how to manage long-tail latency. Tip number 1, before you do anything, look to reduce the number of RPCs before optimizing your algorithms. So many times I've talked to people where the first thing they want to do is go and hunt through their code through every single n-squared algorithm and try to clean that up into some n-log n or even fancier set of code. And that's usually not what speeds up your application the most. The number of RPC calls every single request makes is usually the #1 contributor to slow performance. And for this particular example, this is a really common thing I see where people are making a bunch of memcache or data store calls, and they don't realize that you can actually batch these together. Datastore provides really nice mechanisms for retrieving data via a batch operation where you're able to pass in a set of keys as opposed to each one individually. Tip number 2. Cache read-only third-party API calls. The thing to remember is that if you're making a bunch of calls up to Facebook, Twitter, Google Maps, whatever, they have the same performance characteristics that your application has as well. So realize that for every 100 calls you make, 99% of them are going to be very fast. but there is a chance that a few of them are going to return very slowly. They could either time out or they could just take a long time to return to you because they have the same latency curves just like you do. Even worse, if you start to load a page that chains a bunch of these together, say like an account details page that wants to show name, address, billing information from all these different services, you're increasing the percentage chance that one of these services is going to return slow. And if your page happens to block on showing that information, well, then you end up in a little bit of the problem. So the tip here, when you can, if you have some data that is not likely to change very often, is read-only, cache that locally. Name and address are really good examples where you don't necessarily need to make API calls for all of that stuff. Store it locally, make the retrieval faster, and try to reduce the number of external dependencies your application has. And then the last one, this is sort of a no-brainer, but I like to remind people because not everyone realizes that we have asynchronous methods for almost every single one of our outgoing calls in App Engine. The synchronous methods have an async counterpart. So really learn the documentation, be aggressive about using the async, put in a pretty aggressive deadline limit. You can actually specify how long to wait before a particular RPC call is returned. You can be a lot more aggressive in sending out a few of those just in case one of them happens to return slowly. And with that, Mandy's going to talk to you guys about, once you have everything up and running, scaling out fast so that your application can handle a lot of load.
Thanks, Wes. So what do you do when you have to scale for a one-off global event involving one of the biggest social media entities on the planet? Okay? How many of you have heard of One Direction? Come on. How many of you have heard of One Direction? All right. There wasn't many hands up, and I think most of you are liars. You've all heard of One Direction, you just want to miss it. Right. So back in October of last year, we received a request from our marketing team to assist an agency with the development of a second screen application for what was known as One Direction Day. And One Direction Day was a 7-hour continuous YouTube live stream by the boy band One Direction. And we were told in October, the event was on the 23rd of November, that it wasn't a huge amount of time to get this done. Also, scale was a particular concern because based on previous live streams that they had done with the band, they estimated a potential concurrent usage of 650,000 concurrent users. So because of the two factors, the short amount of time involved, and also because of the scale involved, the agency chose to use Google App Engine. So this is what they built, very simply. The user would connect to the App Engine application and would be asked to log in using Google+ sign-in. Once they logged in, they would be presented with questions. New questions will be available every 10 minutes, 6 questions every hour, 42 questions in total, and there's absolutely no significance in that number, 42. So they were presented with questions every 10 minutes, and they would answer the question. The client-side code would return the answer to an endpoint running in the same application, an endpoint that was designed to handle all of our data services. And that data about, well, any correct answers, only correct answers, were stored into Memcache, along with any demographic information that we have that the user had allowed us to actually gain from the Google+ sign-in. Now, we stored it into Memcache, but because this was a one-off event, we didn't actually store it through to our backend store. So this wasn't a write-through cache. This was just stored into cache. Now, App Engine has a shared Memcache service. A service is completely free. They're shared across all applications running on App Engine. Obviously, that would make it a little bit volatile. So we have this feature as well in App Engine called dedicated Memcache, which is what we use for this event. We reserved about 20 gigabytes of space in Memcache, specifically for our application. So all of the data was stored into Memcache, and there was another endpoint that's not shown on the diagram that was used by the organizers of the event to query that data that was stored in Memcache. And that allowed them to come up with interesting statistics, such as 95% of people in the age range 20 to 30 in Brazil answered the last question correctly. They could then put that data on tickers at the bottom of the live stream and broadcast it live. After the 42 questions had been delivered, we would drain the data. After the event is finished, the data will be drained out of Memcache into Cloud SQL, which is our MySQL in the cloud offering. That's the application. That's how complicated it was, or not complicated. So obviously scale was a big concern, and we, in partnership with the agency, did some load testing before the event, did lots of load testing before the event, up to 10,000 queries per second. And queries per second are what we use internally in Google. Generally equates to requests per second. And that was great, 10K queries per second. The URL of the application was leaked before the event. So we were able to see a steady ramp up in traffic. It was leaked through social media, so that ramp up was relatively exponential. But it did allow us to test some assumptions and also to fix a couple of issues that we saw with our API quota around Google+. We didn't leak the URL, but if I was ever going to do this again, I would definitely leak the URL myself, just to make that happen, because it was great. Then we settled into this steady traffic pattern, where we saw every 5 minutes a peak of about 600 and a peak of about 700 queries per second. That's what this graph shows here. Now, we had to try and avoid the issue where potentially 650,000 users would all answer a question simultaneously. So the delivery of the questions or the availability of the questions was staggered over a period of time. And that's why we have 2 spikes and why the spikes are reasonably broad. So that went on for about 4 hours. And about 4 hours into the event, the organizers of the live stream decided to announce the application live on the event. And that gave us this spike here, slightly different x-axis here. We saw a spike of 9,000 QPS. And later on, we saw a spike of around 5 or 6K as well. So that was fine. We'd tested up to 10,000 queries per second. We had capacity to go way beyond that as well. So that was fine. We had no problems with that at all. And we had no problems with this because App Engine just scales inherently. There's not a huge amount a developer has to do to actually scale an App Engine. Obviously, with an event of this size where we have to scale massively and rapidly, there are certain things we have to do within the application to make sure it doesn't bottleneck or anything like that. But generally, if you're building an App Engine, you'll just scale. The instances, it's very small micro virtual machines, are spun up very quickly, torn down very quickly. So you always have what you need when you need it, but you only pay for what you use. But how do you scale Compute Engine virtual machines? So Compute Engine is our infrastructure as a service offering, where App Engine was our platform as a service offering. And we're trying to blur the lines between infrastructure and platform. So how would you go about scaling Compute Engine virtual machines? So you do it this way. This is something that we announced back in March of this year. We announced Deployment Manager, replica pools, another thing called resource views, which we're not going to talk about too much today. They're a little bit obscure. But basically, we like doing things in Google declaratively. We like creating templates or config files and building stuff from those templates and config files. So this is an example template. It's not really there for you to read, but this is an example of a template. That will be fed into a service called replica pool. And replica pool would do all of the work in converting that template into a deployment, which would look something like that. So this is a group of virtual machines. These are what Chris Ramsdale would call a fleet of homogeneous virtual machines. And they're all the same. They're all identical. They're all built from this template. There's no snowflake servers here. And we have a load balancer as well configured to distribute the load across the pool of virtual machines with a single endpoint, a single IP address you can connect to. So for all intents and purposes, they look like one virtual machine, but there's many. Replica Pool also offers a monitoring service as well. So it can monitor the health of these virtual machines. And if they break, they can bring them back up again. This is all done through an agent running on the virtual machine. OK, so that's a replica pool. This is a static resource. We can scale it manually. We can add replicas. We can remove replicas and size the pool manually. But how would we manage autoscale in this situation? So now we're going to talk about something called Autoscaler. Autoscaler is already available as part of Deployment Manager. Ultimately, it will be made available as a separate API. But Autoscaler allows you to create a config within your template that sets up autoscale parameters. At the moment, the only thing we can autoscale on, and this will change, the only thing we can autoscale on is average CPU utilization across the entire pool. And that's what you'll see there where it says target utilization 0.5. That's effectively 50% target, 50% CPU utilization averaged across the entire pool. So whenever we go above 50% utilization on average, we'll spin up new instances. Whenever we go below 50%, if we have too many instances, we'll turn them down. That's how Autoscale works. And now we're going to give you a demo of that actually working. So this is the kind of demo you can spend 30 minutes on. So I'm going to try and do it in 3. Can everybody read that? Can everybody read it? Yeah? No no's? Okay, good. I should have asked if anybody couldn't read it. Okay, so back to my slide just briefly. I just wanted to set that up. So I'm going to go through the left-hand side of what this demo looks like, and then I'll go through the right-hand side once I've kicked it off. It takes a little bit of time to run. So we're going to be making use of Google Cloud Storage. Google Cloud Storage is an object store. It's a bucket-based store for unstructured data. It has a lot of really nifty, sorry, that's a British term, a lot of really cool features. A lot of really cool features that you can make use of. One of them, the one we're going to make use of, is called object notifications. So we have these buckets. We have an input bucket and an output bucket. So what we're going to do here is solve a relatively complex problem whereby a user has a large number of images coming from some source that she wants to convert into thumbnails. And she wants to do this very quickly. We don't know why she wants to do it very quickly, but she needs to do it very quickly. So that's the problem we're going to solve here. So we have an input bucket, which will receive incoming images, and an output bucket, which will receive thumbnails. So having said that, I'm going to kick the actual copying over of images off now while I talk. So Cloud Storage has this tool called gsutil, and it allows us to copy files from one bucket to another. So in this case, I have a bucket that's pre-configured with about 1,111, well, about exactly 1,111 images, which I'm going to copy over from that bucket to another bucket. So the first thing we need to do here, though, is look at what we have to begin with. So if I go to the developers console, which Wes showed you earlier, this is my replica pool, which I created before. I've actually set this replica pool up with a load balancer with one virtual machine. And this is the virtual machine, IO14 demo Y598. That's all we have. You can see from the spikes on the graph that I have been practicing this demo many, many times over the last few days, which is quite fun. And it's always worked. So hopefully today it's going to work as well. So what else do we have? We have cloud storage. Now look at cloud storage. We have 3 buckets. We have our images bucket, which is where the input images are going to come into. And we have the thumbnails bucket, which is where the thumbnails will be written to. Then we have the payload bucket. And this is where all of the images are. So this could be any source. This could be some source of images, a stream of images, a batch of images, but we're basically going to copy them over from one bucket to another. So gsutil allows us to do that. It allows us to copy from one bucket to another. So we're going to copy from autoscale-io-payload all of the files into autoscale-io-images. And we're going to do this in parallel. We're not going to pull the files down and then push them back up. It's just going to copy them between the cloud storage buckets directly, right? Internal Google infrastructure. And we're going to do it in parallel. Because for some reason, this always seems to fail, I'm going to do this first. ulimit -n 10,000. That allows me to have 10,000 file handles. And for some reason, that seems to reset itself every now and again. I have no idea why. So now we kick off the copy, and that will happen in the background while I continue talking. Is it more interesting to watch this or to listen to me talking? I'm not sure. OK, so going back to the slides, what we have here is object notifications. So object notifications are really cool. Whenever anything is added to the bucket or anything is updated within the bucket, any object, a notification will be fired. And that notification will be in the form of a URL that's being called by the notification. Now, so every image we add to the bucket, we're going to have one of these calls specifically for that image to a URL, which we've registered ahead of time. Now, that URL could be a load-balanced pool of replicas, a load-balanced pool of virtual machines. But that gives us no control over the way in which data flows into the system. So we're going to use something in App Engine. We're going to use an App Engine application and something called task queues. How many of you have heard of task queues? The task queues are one of the best features of App Engine. They allow us to actually do work outside of the user request. So the request deadline for a user request is 60 seconds. Often you want to do work outside of that, so you'll use a task queue. And what you do is you create a task, you put it onto a queue. And then you have something in App Engine consuming those tasks from the queue at a rate of, by default, 5 every second. The application that's consuming those tasks will process the request and then create a request, another HTTP request, to our pool of load-balanced virtual machines. And this will be distributed across our virtual machines, hopefully in a round-robin style, across all of them. We only have one to begin with, so there's not much to distribute. But hopefully we'll have more before the end of the demo. Then we have a process running on the virtual machines that will process the images with ImageMagick and create a thumbnail. So we go back to the developers console, look at that. First thing we'll look at is the thumbnails bucket. And hopefully when I click on this, we'll see a whole bunch of thumbnails, which weren't there before. So these are the thumbnails. The thumbnails are a picture of me. Because I'm an egotist. Or something like that. So we're getting thumbnails. That's good. We want to get thumbnails. What about these virtual machines, though? How many do we have? We have 2 currently. So we've doubled the size of our pool. We've added another virtual machine to do processing. So this basically is set up to a threshold of 0.3, which is 30%. So we're looking for 30% CPU utilization. The application running on the virtual machines is a Go application, and it's using Go routines, so it can do the request processing in parallel. Normally we get 4 virtual machines. Today we've only got 2. It really depends on how quickly we can pull that data down, suck it down from one bucket to another. So let's see what happens and see if we get any more. So now we've got 4 virtual machines. So now what we're going to do is go back to the slides and look at one I created earlier in real Julia Child style, as Julia would tell me. And we have this graph, which shows you CPU utilization, the blue bar, against number of virtual machines. Now, obviously, this wasn't for this run. This is a run I did on Saturday. And you can see that as we hit 30% threshold, we spin up a new virtual machine. We spin up more virtual machines. The CPU utilization has come down. At some point, we say we have too many virtual machines, so we remove them. Obviously, you don't want that to keep happening bang, 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 bang. So you have this cooldown period where you can say there has to be a minimum of this time between requests, between autoscale activations. And that's what happens. And that's the demo. We'll come back to it later if we have time. So I just want to share a couple of tips with you, as Wes did, with measuring fast. A few tips on scaling fast. So the first one is always to use Google App Engine as the entry point for your web applications and as the API service for your mobile and gaming backends. As we've seen with the example of One Direction Day, App Engine scales extremely well and extremely quickly. And there's very, very little work on your part that you have to do. Now, some applications aren't best suited for App Engine, and in that case, you can use modules, build a modular application where all of your front-side stuff is on App Engine, but managed virtual machines being managed by App Engine are running your back-end code. That's really easy and simple to set up. Also, make use of edge caching. So we've seen that with Andromeda, we have much higher throughput, particularly on larger instances, but throughput always involves latency. So any kind of movement of stuff through the network will involve latency. So the best thing to do is cache your content as close to the user as possible. And you can make use of edge caching, which is caching in our data centers or with ISPs, because we have a global peering relationship with many ISPs. And you can do this with App Engine using static content, with cloud storage by setting cache control headers on any data you store. And with App Engine, again, you can do it on dynamically generated content by setting cache control headers on the response stream. And very quickly, because we're running out of time, I'm going to run through these very quick. But network I/O intensive workloads make use of those big virtual machines for more network throughput. For scaling, App Engine can sometimes do with some help for scaling, and you can use idle instances on App Engine to make it scale that little bit better. Idle instances effectively answer requests when there's no instance available to actually answer that request immediately. So they're there really as a backup to answer requests. And the final one is to take advantage of features such as page speed and memcache. Page speed effectively is an App Engine application or an App Engine service that's free to anybody who has a paid application, have set billing up on their application. And it will optimize your HTTP requests. It will compress and cache data. And it provides services such as inlining and critical path rendering. Memcache, you guys all know how to use memcache. But you can also take advantage of dedicated memcache, as we did with One Direction Day. So we've seen that Google is built on a culture of fast, and that we're constantly driving innovation within our infrastructure in order to maintain and improve performance across all of our APIs and services. We've also seen the Google Cloud Platform benefits from this innovation through network stuff like Andromeda. Sorry, I forgot what I was going to say there. We've also seen that long-tail latency is an issue, and it can be addressed with the ability to measure fast, as Wes showed you. And we looked at tools such as Cloud Trace that allow you to actually gain rapid insight into issues, that kind of issue running in applications in the cloud. And finally, fast matters. We come back to the message that Wes had initially. Fast matters, fast will always matter, and Google Cloud Platform can help you build applications that run fast in the cloud. So what are you going to build? With that, we're going to sign off. We've only got a couple of minutes of questions. The call to action, go to the Cloud Platform blog and find out about features that Wes talked about and that I talked about. Preview features such as Deployment Manager and Replica Pools. You can sign up there. The next session is in room 7, Zero to Hero with Google Cloud Platform with Chris Ramsdale. You can provide feedback via the QR code. There's one up there on the board. And you probably haven't received anything about this yet, but you can get $500 in credits for the Google Cloud Platform. Go to g.co/cloud starter pack and enter the promo code GoogleIO. And there's also a roadshow in the US happening very soon. And you can go to googlecloudroadshow.com to sign up for that.
Great. And if you guys have any questions, Mandy and I are going to be sitting outside in the cloud booth over there. So come find us. Thank you very much.